Welcome back everybody to MrMiers Math Channel. Today we're going to continue on the exponential and logarithmic functions chapter, and we're going to talk about section 8.2, which is exponential decay. So we're going to be graphing exponential decay functions. All right, so let's get talking about the function and the graphical features themselves. So as we know before, y equals a times b to the x power is an exponential function, where a is greater than 0, and for an exponential decay function, what we're going to be talking about is the fact that b would have to be in between 0 and 1. So let's take a value between 0 and 1, like 0.75. All right, b is the value that we repeatedly multiply by in this exponential function. So if we continually multiply by 0.75, that being less than 1 is going to give us a value that's less than our existing value. All right, so if we multiplied something by 0.75, it would be 75% of its value from before. All right, in terms of characteristics of the graph, however, this graph is going to fall from left to right. Okay, it falls because it's getting smaller as we're going from left to right, just like we read. The domain is going to be all real numbers. We can plug anything into this function and we'll get an output value out. And then for the range of the very basic exponential functions that we're going to cover, we would have y is greater than 0. The only time that's affected is when the starting value is affected, and maybe we see something that dips below the x-axis. All right, so let's get into our first example. Here we go. Clear the board here. All right, so we're going to graph the function y equals 1/2 to the x power. And of course, we're going to talk about these features later. What I want to do is get to the graph right away, create our t-chart, and then we'll go back and answer some of these questions about the horizontal asymptote, domain, and range. Once we discover what's happening here, then maybe we can use the function to figure out those features even before we graph it. All right, so I'm going to make a little t-chart here, and I'm just going to choose some random values. All right, obviously I've thought about this beforehand, but we're going to just choose some values that will actually appear on our graph. When first encountering a new function and a very basic function of that type, usually we use values like -2 to +2, things like that, just to see what happens, you know, of that function of a new type. So let's plug in -3 right away. All right, so if I plug in -3, that would be 1/2 to the -3rd power. All right, that whole thing to the -3rd power, and we could simplify that as 2 to the 3rd power, and that would give us 8. All right, if we plug in -2, that would be 2 to the 2nd power, which would be 4. We plug in -1. Remember that negative exponent. To get rid of it, we just flip the fraction, so that's 2 over 1 or 2, and then to the 1st power, which is just 2. If we plug 0, we don't even have to write this one down. 1/2 to the 0th power, just like anything to the 0th power, is 1. And then 1/2 to the 1st power is just 1/2, or 0.5. Okay, now let's plot those values to see what happens. -3, -8. Sorry, -3, +8. -2, 4. -1, 2. 0, 1. 1.5. So we can see as this goes from left to right, this thing is falling, and it's approaching some value that it will actually never reach, which is that asymptote. Now in this case, with this being a very basic function of this type, that value that it's approaching is 0. All right, we're going to get smaller and smaller, and yeah, this isn't the best graph, but there we go. We're going to approach 0, but we're actually never going to actually reach 0. All right, the reason why we're never going to actually reach 0 is what we're doing is we're multiplying by 1/2, or in other words, we're cutting that value in half every single time. So let's say we started at 8, we're cutting that value in half, we get to 4. Then we cut it in half, we get to 2. Cut that value in half, we get to 1. And continue that process. All right, as we continue to cut this value in half, we're still going to have something left over. So we're never going to actually reach 0. It might be something that's incredibly close to 0, but even as we approach infinity over here, it's never going to actually reach 0. So now let's go back, talk about the horizontal asymptote, the domain, and the range. So the horizontal asymptote, like we stated before, is that value that we're continually approaching. That's y equals 0. Okay, and I'm going to go back here really quickly, clear the screen and go back. Whoops. So y equals 0, here we go. Y equals 0 is that value that we're continually approaching but never reach. The domain, like we said before, is all real numbers. We can plug anything in, all right, really big positive value, really big negative value, decimal values in between. We can plug any real number into this function and we'll get an output value. And then for the range, from that graph, everything was positive, all right, and it was greater than 0. All right, so we're going to have y is greater than 0 for the range. All right, the horizontal asymptote is going to be key in figuring out the range, okay, because that horizontal asymptote is that value that we continually try to reach, okay, and no matter what this thing looks like, all right, that value that we're getting closer and closer to is something that we're never going to actually touch. So the range definitely has to do with that value. All right, so let's move on, get to the next example. All right, in this case, we have 3 times 1/2 to the x power. Remember, just like before, all we're doing is just making small minor adjustments to this function. We're just going to add something, change some values, and see what that does to our graph. All right, so we have 3 times 1/2 to the x power. So first thing that we're going to do, let's make our t-chart just to see what happens here. And I'm going to choose values -2 to +2. Stick with the basics here. All right, now let's plug in -2. So we have 3 times 1/2 to the -2nd power. The first thing that we got to do is apply that exponent. So we have 1/2 to the -2nd power, which would be the same thing as 2 to the 2nd power. Now actually apply that exponent here. So 2 squared is 4. So then we have 3 times 4, which is 12. All right, then let's use -1. If we plug -1 in, this would be 3 times 2 to the 1st power, which is just 3 times 2 or 6. All right, plug 0 in. Anything to the 0th power is going to be 1, so that's just 3 times 1, which is 3. All right, now in the positive values, we have 3 times 1/2 to the 1st power. Well, that's just 3 times 1/2, or 3/2, or 1.5. All right, now with 3 times 1/2 to the 2nd power, 1/2 to the 2nd power would be 1/4, and then we have 3 times 1/4, which is 0.75, or 3/4. Now let's approximate these values and draw our graph. Obviously, -2, 12, that would be way up here. Right here, maybe going off our graph. We don't have to plot that one, but I'm trying to just so that we have it on our graph. -1, 6, 0, 3, 1, 1.5, and then 2.75, about 3/4. Okay, 3/4 of the way up from 0 to 1. Now drawing that function, here we go. Doing my best here. All right, and this thing is going to level out. And once again, since 1/2 is the value of b, so right there, there's 1/2. That's what we're repeatedly multiplying by. We're just cutting that value in half every single time. And since we're doing that, we're approaching 0, but we're never actually going to reach 0 in this case. All right, so it gets smaller and smaller, gets cut down by half every single time. All right, and that's a pretty rough sketch of our graph. All right, of course, that value that we're approaching, like we said, is 0. All right, the domain is all real numbers. We can plug anything in. All right, the reason why we don't see anything over here is just because it's so far up above the level of this graph here. And then finally, the range. Everything's in this positive sector here, so that would be y is greater than 0. So I'm going to go back and just fill that in for those that are taking notes here. Oops, thought I hit the pen. There we go. So y equals 0, all real numbers, and y is greater than 0 for the range. All right, moving on to example 3. All right, in this one we have y equals 2/3 to the x power plus 3. Now once again, like we talked about before, we have to figure out, is that plus 3 directly affecting x or affecting the overall function? And in this case, that plus 3 is on the same level as this 2/3, so it's affecting the overall function. You know, we're not adding 3 first to x and then using the exponent. We're going to figure out what 2/3 to the x power is first and then add 3 to whatever value that is. All right, so that means this is going to cause some vertical shift to our function, to the graph of this function. All right, so I'm just going to plug in a few values. We're going to get a lot of decimal values here, so I'm just going to plug in -2, -1, 0, and 1, and we'll see what that looks like. All right, so for -2, we have 2/3, all right, that quantity to the -2nd power plus 3. All right, if we evaluate, we would get 9/4 plus 3, which would be about 5.25. All right, if we plug in -1, that would give us 3/2 plus 3, and that would give us about 4.5. If we plug 0 in, this one's rather simple. Remember, anything to the 0th power is just 1, so that's just 1 plus 3, or 4. And then if we plug in 1, we have 2/3 to the 1st power plus 3, which is just 3 2/3, or 3.67. I'll round to the nearest hundredth there. All right, now let's plot these values. -2, 5, and 1/4 there. -1, 4.5. 0, 4. We can see it's already starting to level out at this point. And then 1, 3.67, which is 3 2/3. All right, and it's going to level out. All right, remember from the previous section, what's happening to the overall function is going to affect that horizontal asymptote. So that value that we're continually approaching is +3. All right, so that means, let me just undo that box there. There we go. All right, that means as we continue to the right, we're going to be approaching +3, but we're never actually going to reach it. All right, and then going up this way, we could find other values on our graph, or we could just approximate how this thing would look. So we have exponential decay, falls as it's going to the right. And then going back to our horizontal asymptote once again. Whoops. Keep forgetting to go to the pen. Our horizontal asymptote is y equals 3. The domain is all real numbers. We can plug anything in and get some value out. And then any real number in and get some value out. And then for the range, this thing was greater than 3, like we saw in the graph. All right, moving on. So now in example 4, we have 1/2 the x minus 2. All right, and notice that -2 is up in the same level with x. So that means in terms of order of operations, this -2 is in the exponent spot, which would mean if we were to evaluate for a particular x value, we would have to subtract 2 first and then figure out 1/2 to that power. All right, so that means that this -2 affects x directly. So if it affects x directly, that's going to cause some horizontal shift. All right, and we'll figure out from this graph where that horizontal shift occurs. Obviously, it has something to do with 2. You know, either 2 to the left, 2 to the right, one or the other. All right, so making our t-chart here, I'm going to plug in numbers from -1 to 3. Now let's start with -1. We have 1/2 to the -1 minus 2. Well, -1 minus 2 is -3. So that's 1/2 to the -3rd power, which would be 2 to the 3rd, or 8. If we plug 0 in, don't just automatically think 1 here, because we're plugging it in for x. We have 0 minus 2, so that would actually be -2. So 1/2 to the -2nd power would be 2 squared, and 2 squared is 4. If we plug 1 in, we have 1/2 to the 1. There we go. 1 minus 2, which would be 1/2 to the -1st power, which would be 2 to the 1st power, or 2. Now, once again, we don't have to go through all these processes to fill in the rest of the table. We can see the pattern that's happening, and if we know conceptually what's happening in the equation, we can fill in the rest of the table. Over and over, we had our starting value, and with b as 1/2, this value gets cut in half every single time. So that means this is going to be 1, and then we're going to have 0.5 or 1/2 there. Now let's plot those points. And here we see that our value that we're starting with is much higher. That value that intersects that y-axis, our y-intercept, is much higher than previous examples. So that's what happened. That's what that -2 did. It shifted this graph to the right 2 units. All right, so let's just draw the graph and that value that we're continually approaching. Since there's nothing adding or subtracting to the overall, the general function here, that value that it's approaching is 0. All right, let's go back and let's fill in that little chart there. Oops, a little too far back. All right, so our horizontal asymptote was y equals 0 once again. The domain was all real numbers, and then the range was y is greater than 0. All right, we've got a few examples to go here. All right, we want to classify the function as exponential growth or decay. Now, with the last 2 sections, we should be able to do this pretty easily. The key thing here is, what is b? All right, if b is greater than 1, it's going to be talking about exponential growth, all right, because we're going to repeatedly multiply by a value greater than 1, causing that thing to get bigger. All right, if that value of b is in between 0 and 1, that thing is going to be decay. All right, because if it was something like 0.5 or 1/2, that value is going to be repeatedly cut in half over time. All right, so we just have to identify what b is. So in part A, b is 2/7. That's in between 0 and 1, so that's exponential decay. All right, for part B, b is 3. That would be greater than 1, so that's growth. All right, with our fractions, make sure to be careful. 5/2, that would be about 2.5. That's greater than 1, so that's exponential growth. All right, 3/5, that's in between 0 and 1. All right, 0.6, so that would be exponential decay. Okay, in the last example, we want to figure out which function's graph is shown below. Now, what we're really going to be doing here is trying to figure out if we can gain any information from the graph to match up the graph with one of the functions in the options that are listed here. What we want to look for is can we determine anything, about an exponential function from the graph? Can we determine A? Can we determine B? Can we determine anything that's coming after the function if something's happening up here, okay, or adding or subtracting to the overall function? So those are the features that we have to look out for. All right, so things that we could think about is what would be the horizontal asymptote of this function, or what does it appear to be from the graph? And if we notice, this does not appear to be approaching 0. Okay, it is leveling out here, and it is approaching some other value besides 0, or at least that's what it seems. So it seems to be approaching that value of 2. Now, if you know that, then this is easy. Okay, we can see that plus 2 there. That would represent the horizontal asymptote, or the HA, as we call it. So that might be enough to say that, okay, our solution is D. Another thing to look at would be the value of B. Now, we just talked about the difference between exponential growth and exponential decay, and notice one of these is talking about exponential growth. 5/4 is bigger than 1, so that's talking about exponential growth, which is something that we don't see in this function. All the others are talking about exponential decay. So that'd be an easy way to get rid of one of these options. Okay, limit the options that we have available for us. All right, so that's it. If you liked it, hit the like button, subscribe, and like always, have a great day.